Bismillahirrahmanirrahim. Greetings. In the previous lecture, we investigated about the limit of f of x, where f of x was x squared minus 4 over x minus 2 as x approaches to 2. And then our first guess was that the limit does not exist because we end up with 0 over 0. And then we change it into product form, and again we end up to limit does not exist because we end up with 0 times infinity, which both of them were absurd. So we were tempted to conclude that limit does not exist. But as a student of mathematics, we don't just give up with one or two to try, we try other ways. So we went to numerical method, and we went through the chart, and we found out that yes, our guess for the limit not to exist was incorrect. The limit does exist, and it is in fact number 4, is 4. And that also proved to be the case when we approached it with algebraic manipulation. And the limit in that case also ended up to be 4. Now, in this lecture, we are going to investigate two other kind of functions that in this function, the limit does not exist. The limit does not exist, but in two different ways. So let's get started, shall we? Okay, let me see where I have them. We want to know what is the limit of f of x, where f of x is the absolute value of x minus 2 over x minus 2. So the concept of absolute value is very elementary. Absolute value of x is x if x is a non-negative, and in negative x is negative. That's exactly what we're applying to that. I'm not going to deep into that. Now, this we can use it numerical method, which means we can make a chart and see what will be the limit as we did in the previous lecture. But that one I leave it as a homework for you, and try it please. It's very good exercise. This one I'm going through algebraic manipulation and see what will be the limit. Now, what is the difference between x and a constant is that the constant number does not assume any other values. For example, we don't say let 7 to be 8 or let 7 to be 6 is nonsense. Huh? But x is a number but can assume different values. We can give different values for the x. Now, the values that we give to x for this function, for this ratio, if those values we give to them is to the right of 2 and we approach to 2, then what happens? Then that will dominate 2. Like for example, if it is 2.1, 2.1 minus 2 is a positive number. So the numerator stays as x minus 2, denominator is also assuming the same, they are the same x, therefore the ratio of them will be 1. You follow that? That is in case if I'm selecting what numbers to the right, the x is assuming values from to the right of 2. Now, what happens? X assumes values to the left of 2. Then what happens here? These 2 will dominate that x. Is that right? For example, if x is 1.9, then 1.9 minus 2 is what is a negative number, negative 0.1. Is that right? So what happened here, the numerator will be negative, and then absolute value cannot be negative. If it is negative, you multiply it by negative, you make it positive. So that will be, you multiply this one by negative, then you take it out of absolute value, so that will be negative x what minus 2 over x minus 2, which is negative 1. That is one way to interpret that. The other way to interpret, because you are selecting values for x, you are giving values for x to the left of 2, therefore 2 minus x will be a positive number. I have written that, huh? Your 2 minus x will be a positive number if you are selecting s to the left, to the what? To the left of that. So hopefully you are clear with that, huh? Again, I repeat myself, if you are selecting values to the left of 2, then 2 minus x will be a positive number. So any value you give to x, in that case, 2 will dominate that, the signs of that. For example, you give 1.9, then 2 minus 1.9 will be what? Will be a positive number. That's exactly what absolute value means. So in that case, will be 2 minus x over x minus 2. Then you can multiply numerator and denominator by negative 1. So it becomes x minus 2 negative to the next to the fraction divided by x minus 2. And x minus 2, they are approaching 2 with the same rate. With the same rate. So the ratio of them will be 1 no matter how far you go. So that will be what? In this case will be negative 1 no matter how far you go. Okay, then, so the answer will be positive 1 and negative 1. And now, let me also have the graph of that. Let me also discuss it through the graph. So in that case, we say that because limit should be unique, uniqueness is very important in mathematics. Should be unique, that in that case we say limit does not exist at x as x approaches 2. Okay, so the graph of that, as you see, is very explicit. You can see it for yourself. When x is approaching to 2, it's always equal to what? 1. And when x is approaching to 2 from left-hand side, it's always negative 1. And since these two limits are different, therefore the function, the limit does not exist at 2. All right? And now, now the other thing is that not only the limit does not exist at 2, the difference between this and the example that we had, x squared minus 4 over x minus 2, is that there was only one hole. The graph was all same. You remember, g of x was x plus 2. There was a whole 1 point. So we say that that has a removable discontinuity. That is something aside that you will be seeing when we talk about continuity of function. But in this case, this function does not have removable discontinuity. This is too far away. You can see that. Okay, so this is clear for you, and the graph is that. Now let's go and investigate another kind of function that the limit of that does not exist. And that will be this one. Now my function is 1 over x minus 2 quantity square. So I know the denominator is always non-negative. And the denominator cannot be 0 to begin with, because we will not be dealing with number. So as x approaches to 2, we know the denominator is always not positive. The numerator 1 definitely is a positive number, positive over positive. So we are expecting that the graph lands above the x-axis. That's the first observation we made. Then, using numerical method, as I have done that in the table, we notice that as x approaches to 2, doesn't matter from the left or from the right, the value of the function keep going up and becoming bigger and bigger, but above the x-axis. The chart is saying all of them, is that right? So I'm approaching to 2, I start from 2.1, then I start 2.01, then 0.2001. So I'm making a smaller and smaller, closer and closer to 2. And then I start from 1.9, then 1.999, then 0.19999. You can even put some more values, and then give the value to the x minus 2, subtract from 2, square it, divide, etc. I have done all of this, and you end up the function, the value of function of x, it keeps going up. You see that? First was 10 squared, then become 10 to the 4, then become 10 to the 6, then become 10 to the 8, 10 to the 10, 10 to the 12, and in chemistry they call it Avogadro's number. He passed from Avogadro's number become an atom. He passed all of them. So then the sketch of the graph of that will be this one. So it's very explicit, I don't even have to mention it. As you can see, the graph is going to infinity and above the x-axis. Okay, then I thank you for watching. The purpose of this series of lectures is about first of all, we would like to enhance ourselves about the concept of limit, and then when we go to the delta epsilon definition of limit, which is a bit abstract and difficult, we have some good idea already. Then I start to also gradually to kind of digest that definition. But after we kind of be comfortable, maybe through graphic, we can use some kind of visual aid, like drawing and graphing, and see what we mean by delta epsilon. And once that one is achieved, then the theorems that follows that should use the definition to prove it, that give us more muscle about the subject. And then when we solve one or two examples, then once and for hopefully we will overcome the difficulty with rigorous and abstract mathematical definition of limit. Is known as epsilon delta definition of limit. Okay, then I thank you for watching, and as always I wish you all prosperity and good health, and please stay safe. So long.